just before we start, okay, thank you. So just before we start, if we could use a show of hands, I'd like to know how many persons here are new to machine learning. Could you just indicate by raising up your hand? Ooh, okay. Okay. So, that in that case, I was just going to dive into code, but I think I'll just do a presentation first before we jump into the code to carry everyone along. One more thing. Can everybody, who cannot program, write a code with, say, Python or Java? New to programming, cannot program? Could you please raise a hand? Okay, great. So I assume everyone here can program, so that is fantastic. So we would just do a brief introduction to machine learning, and then we'll run into the code. So let me share my screen. I think I'll start with the presentation. Okay. Okay. So briefly, I'll talk about an overview of machine learning, speak on the principles of supervised learning, and then we would talk a bit about deep learning, and that's when we'll run into the code. So there are two popular definitions out there. The first is that ML is what gives, and it's an old definition in 1959 by one of the pioneers of AI, Arthur Samuel, that machine learning gives computers the ability to learn without being explicitly programmed. And that's a very interesting assertion. Can a computer learn to solve problems without a step-by-step instruction set for the computer to follow? And that's the catch of AI in general, but in particular of machine learning from data. So I think I can put that out there, that without data, you do not have machine learning. Tom Mitchell defines machine learning as learning from experience to improve performance on a task. So when a computer learns, it's trying to make inferences. It's trying to generalize to new examples from data. And we'll see shortly that we are going to contrast between generalization and memorization, because the goal of the computer is to learn from a sample so it can say something with a particular degree of accuracy about the real world or about the population. Okay. Now, there are three broad schemes of learning in machine learning, actually, three broad components of machine learning based on the approach to addressing the learning problem. And these schemes are the supervised machine learning, the unsupervised, and the reinforcement learning scheme of algorithms. In the supervised learning framework, every data point or observation is associated with a label. That is to say, you have a target, you know what outcome you're trying to learn from your data set. Remember, a data set is nothing more but a representation of a real world phenomenon. Okay, so now can we teach the computer to learn using this labeled data? And that's the goal of supervised learning, where you have a teacher that will guide the computer in understanding the patterns from this data. So because why it's called supervised is exactly the presence of those labels or the targets. So with these, we can guide the machine. We can let it know how well it is learning. We can score the machine. So this is a supervised training paradigm to help the machine to make approximations about unknown samples. That is about observations that were not part of the training set when that model is deployed. So this is a, pardon me, this is a illustration of a supervised learning framework where you have a data set and consider each circle as a bunch of as an observation. And you can have a whole lot of these. So you have a set of observations, you have multiple variables, and then you have a target. So in this case, this is a disease classification data set. So we want to know if patients have, say, glaucoma or cataract. Okay, sorry. So we separate the data set into the training and evaluation data set, and then we build a model. The goal of the model now is to minimize the prediction error on our evaluation or test set. So this is what a supervised, in general, at a high level, what a supervised framework, learning framework will look like. The labels help to guide, to assess the accuracy objectively of how the model, or assess the performance. I won't use the word accuracy. Accuracy is just a metric. To observe the performance of how the model is behaving. Okay. Now in the unsupervised framework, you don't have these corresponding labels. You don't have a target. You don't have what the true outcomes are for your learning problem. So it's up to the machine, to the computer, to determine the unknown structure of the data. And it accomplishes this by grouping similar samples together. So we'll come to a similar example. Here we have a group of patients, and each data point is an attribute, a patient with a set of attributes. So we have certain patient characteristics. So the goal here is, are there some inherent structure or grouping among the patients in these data sets? So we can pass in an unsupervised learning model, like your k-means, to try to find the relationship between these observations, these data points, in a multi-dimensional space. The case may be depending on the number of features, but you want to find some grouping in the vector space of the data points. And we see a lot of complex problems where, because collecting labeled data is expensive. So in some problems, we've had to use unsupervised learning to generate our labels. So you have unsupervised learning generating labels. Then you can do some ground truthing to verify the groups that the model has predicted. And then you can use that labels to assign them as targets. Those labels become targets. And then you can do a supervised learning problem that you can objectively measure. So you can see how all these techniques can come together as part of a pipeline of a ML, an end-to-end workflow to solve a problem. You have to be creative in how you want to use these things. Okay, the final scheme, really very interesting, is a reinforcement learning scheme. Here we have an agent. Now think about this agent as an abstract agent. It could be a robot. It could be a data structure. It could be really anything, but some agent is interacting with the environment. Like I was thinking about something a couple of days ago. I won't say too much about that, but I was trying to think, okay, how can we measure climate change? How can we try to learn mitigation approaches for climate change taking into account some of the anthropogenic behavior, that behaviors of humans in a particular environment. So now I'm thinking of there is an agent there. There is an interaction with an environment. And then there's a feedback. And you're trying to learn behaviors. What are the possible set of actions that could be taken in this environment? And what are the responses? And how can we adjust performance on a particular task? In this case, we'll be optimizing whatever that goal is to mitigate the effects of climate change in that community. So it was just a thought, but you could see where that's leading to. So that's reinforcement learning. So it's not restricted to game playing as you have with playing chess or playing Go. Some of you who may have been familiar with the AlphaGo. It's really it's if you can think of a problem and it can fit into this reinforcement learning framework of agent interaction with an environment and improving its performance in that environment on the task. So this is a graphical overview, and you see this diagram. For those of you familiar with RL, you'll see this everywhere. So what we have now, although the way I describe things here is following the RL approach from that began pioneered a lot by Sutton and Battle, especially from the University of Alberta. It's a strong, that's where those professors were, and a lot of research came out from there, where you have an environment interacting with an agent interacting with an environment, and you have the idea of policy and rewards. Now, policy is the mapping of states, and these states are the different what would I call it now? In a sense, the different set of actions or the dynamics, if you will, of an environment, not set of actions, but the dynamics of an environment. You have go from one state to another. And so policy is how do you map those states to the probability of choosing an action in a particular state. And the goal is to have, okay. So the goal is to have what would be the desirability of a particular set of actions in a state long-term. So, and that's the idea of what we call the value function, the long-term utility of states, considering future states. And there is another scheme of learning, not so popular in the West, but it's called the learning automata. I'm just putting it out there because that's what I was involved in my research, but developed from the East, from Russian sciences, pioneered by men like Teslin, Tsetlin, and Krinsky and Krylov. But it's a general idea to learning in a stochastic environment via interaction. A very interesting field of study if you are interested in those things. Okay, but we are going to be talking here, and we'll go into the code shortly, on supervised learning. So a couple of the principles of supervised learning is that there are two broad classes of learning. One is classification and regression. The whole idea of this is classification is that your target, what you're trying to learn, is a class membership of some sort. Does the patient have disease or not? What would the weather be tomorrow? Will it snow? Will it rain? As an example of a classification problem. A regression problem has as the target real valued outputs. So what would the temperature be tomorrow? That's a real value output. What is the pricing of a house in a particular area? That's real value. And but these are just pictorial illustrations of that point of two different data sets, and you have the target variable. One is at the left, I suppose, A, classification example, and then the B is a regression example. And why it's called regression, if you're familiar with statistics, and you know about multivariate regression or linear regression. Simply put, when you're talking about classes of supervised learning, Regression simply means that the output is real value. While it is called regression, I think it has some historical, but it's not. So regression as an algorithm is completely different. It just simply means that, hey, what I'm trying to predict is a real valued number, right? So that's all there is to that. And how do we know when learning has occurred? The goal is to ensure that the machine has generalized the new examples, is able to observe patterns and to learn or to resolve similar but an unseen example to approximate what that outcome would be. But memorization is simply remembering the data or the information that the student has seen. So imagine you write a test and the lecturer gives the exact problem in the finals that was given in the class. Now you could memorize those problems and just repeat it. But if you are given similar but different problems, in the finals, you can use the information learned during the course of the semester, and then the teacher can have an objective measure if you have learned something, if you've learned to think with the information you gathered during the course of the semester. So this is similar to how we assess if learning has occurred. So in line with that, typically we split, and this is why we have to split our data sets, because we cannot evaluate the model with the data that was used for training. Because that's the data that the machine has probably learned the patterns, the structure of that data. It's always good to have an evaluation set. Now, typically we have what is called the validation set and the test set. The goal here is that there's something called hyperparameter tuning. It's just a fancy word to say, okay, you want to tweak some parameters of the model and to see how much you can learn from the data. So when you tweak a parameter of the model, you can evaluate that new model structure on the validation set to know how well that set of parameters performed. But the test set is critical. Before a model goes out to the real world, you have to have a gold standard and what we call a single objective measure, but a gold standard to say for sure what my model is seeing is exactly what you will see when it will go out there. Nothing has seen this data. So you've done your hyperparameter tuning, you have what you think is the best set of parameters that will maximize the learning problem. Then you can evaluate it on the test set before you deploy it. So typically, if you're into research, the test set is what you run. The outcome of the test set is what you have in your paper, and that's what you submit. And if you are in industry, the test set tells you exactly what you will see when you deploy the model, or your downstream APIs, or whoever will be consuming that model. Okay, so I will move. Bias variance trade-off. It's similar to what I've talked about, but yeah, bias simply means that you have learned closely the underlying structure of the data, including the irreducible error. No, I'm sorry about that. That's not bias, that's variance. So bias means that the model was unable to learn the structure of the data set. So take, for example, you have okay, so take, for example, you have, just trying to think, you have a data that is highly non-linear, but you don't know. So you can be training with something like a linear regression model that has a parametric assumption. The model may perform badly because it has failed to generalize. It oversimplified the learning problem. I think we have a graph that explains this. Okay, let's use this one so we can. So if you see the left, no. This is not what I want to see. Okay, let's look at the center, the underfit, where you have a bias. So it's oversimplified the learning problem. So linear regression will plot a straight line, but you see the data has a non-linear kind of structure. So variance, on the other hand, is you've used a spline, you've made a very flexible model that learns intrinsically all the data points of your training set. But when you deploy that model, so the training set looks like this, the example on the right. When you deploy this model, it will perform badly. So the performance suddenly drops on your test set. And that shows you have a variance problem. You have fit too closely your training set. So there's always this trade-off. And the example on the left is a good fit to have that balance between bias and variance. Have a high performance on the training set and a high performance too on the test set. So we want to have that balance, and that's when it help us know really how well the model has learned and if it is generalizing to new examples. Okay, so deep learning, which would be, so the goal, remember, is to lay the principles. So especially those who are new to machine learning, just to lay the principles of ML. It's just quick fire. And so when we go into the code, those things just make sense. So deep learning, it's built on on a particular machine learning algorithm called neural network. And the idea is to mimic how an engineering approach to mimic how the brain works, how the brain cells works using neurons and the rest, and how information passes from one neuron to another. And as it goes, as those information is passed in the brain, you generate higher order representation. But this happens so fast. So your eye sees the picture, and in microseconds or whatnot, the image has formed in your brain. So you're able to perceive the world as you move. But can we have an engineering approach to mimic this behavior of the brain, to learn difficult problems, problems that you cannot, it's tough to have any sort of um, um, instruction cycle. You cannot have a recipe kind of approach to solve it, like recognizing faces. How do you tell if a face is, if it is Grace or Bob? How do you have the computer tell the difference between two faces? Something that a human will do easily. So this is where deep learning comes in. Now, an artificial neural network is composed of three major layers. The primary layers, you will see a lot of variations on this as we go on. The input layer, the hidden layer, and the output. Now, and this is a description of that. And you have a neuron, a cell or a neuron in each of these layers. Now, from an engineering standpoint, the hidden layer is what the whole deep learning comes from. That with more neurons, presumably, you're able to learn more complex representations, higher level hierarchies. So you could solve more difficult problems. And so more of these layers actually just injects more non-linearities, if you will, to your or expressiveness to your model. But be careful because you don't want to overfit. So it's a sophisticated game of trial and error to decide how many layers should be in the hidden layer, what's the number of neurons in each layer. At the end of the day, it will boil down to experience you have in designing your architecture and in trial and error. Run it and see what the result is. There's there's something called the no free hunch theory. That means upfront you cannot tell what will settle for sure the model that will perform best on a particular data. You just have to try it. But I also mentioned a principle called Occam's razor that will say start with the simplest set of hypotheses, and then you can work up from there. So keep it simple. Try to, and then you can add more complexity and see what happens. Okay, so I will, for the purposes of this, because I'm also tracking the time, I think I've gone close to 30 minutes. So I want to have some time for the code. Now, let me just go to the slide and see how much, because I want to go too deep. Okay, so backpropagation is good enough. And the rest of this I can, okay, I think that's even the end. Okay. Maybe I would talk a little bit about backpropagation, and then we can go into the code and we can explain things as we code. So that's better. And you could follow along or fill up a Colab notebook as well. Okay. Oh, you know what? I come to backpropagation when we are coding. Let me not make this too theoretical. Let's just write code, and then when this comes up, we can come back to the slide. Okay, so stop sharing there. And let me just a second. Good. So many things hanging around here. So I will share my screen. Okay. I hope you can all see my notebook. Let me increase the size so that it looks large. Okay. Now they are in deep learning. There are three. How will I put it now? But high level, really, three themes, if you will, of deep learning architectures. One is called the multi-layer perceptron, which is your MLP. If you don't know about it, don't bother. We would just, let me, actually, I want to take this down. Okay. So two deep learning schemes. And then the other is called, which we would work with now, the convolutional neural network. I just thought it's more interesting and while we are building it, you could see the difference between that and the MLP. And the CNN is really the backbone of some of the interesting architectures you've been seeing out there. So for those of you familiar, which I would just, maybe you're talking about transformers and the rest, and this encoding, decoding machines and whatnot. CNN is the backbone for all this, most of the state-of-the-art vision models, like image classification models. So it's really a core building block. And then this other is called the recurrent neural network. So things like ChatGPT taking the world by storm, but RNNs are the building blocks of building this sort of large language models. Okay. So now we are going to use CNN to try to classify, to learn a set of images. So we are going to use a data set called the Cypher10 dataset. And to give some context about Cypher10, it is, so what it does is it consists of about 60,000 32 by 32 pixel colored images. So in 10 classes. So you have about 6,000 images of an airplane, cars, a bird, cats, deer, dogs, and the rest, sheep, and a truck. Now, so 50,000 of these will be used for training in the training set. And remember, I talked about why you have to split into your training set and your test set. And we'll use the remaining 10,000 for testing to see if the computer is able to learn the difference between a cat and a dog and whatnot. So that's the example we would use right now. We're going to build that. So this would be, if you've not done this before, this would be your first ML model or AI model, as the case may be. So let's import set of packages that we would use for this. Of course, this is introduction to machine learning with TensorFlow. So we'll be using TensorFlow, which is a Python package, very powerful for machine learning. And in particular, we would use a high-level API that is now a part of TensorFlow called Keras. some years back, it was apart, but from TensorFlow 2, it became a core part of the TensorFlow framework. This is just, now what we also import is a component called layers. So if you remember the image, I talked about deep artificial neural networks, you have a set of layers. You have the input layer, the hidden layer, and the output layer. And okay, what Keras is. Okay, let's do that. So Keras is actually an API for building these deep neural networks. So let me find something. This because the idea is to make building neural networks simple. It's like it really reduces it into like you're placing building blocks, Lego blocks, one on top of another. So in building deep neural nets, there are many things to configure. You need to decide the number of neurons in the layer, the number of layers, the type of layers, and there are different types of layers, right? In this case, we are building a convolutional neural network. We'll use a convolutional layer. We could also use the max pooling layer. We could add a dropout layer. You could add a batch normalization layer. So there are really a lot of things you could do. Now, building these things from scratch, they are definitely non-trivial. But Keras has provided all this implementation in an API, has abstracted this information, these mathematical details, right? So you simply call the layer you want, pass in a set of parameters you need, and that's that. You get your model to train. So really, it did a great work in democratizing ML, right? So software engineers, people who are really anybody now can build intelligent applications. So if you can understand things from the first principles, the way I've explained it, I explained machine learning. I did not refer to any fancy math, no calculus, nothing. Just explain, understand how learning works. How do you build an intelligent agent? How do you know that the agent has learned? And these are the things that really from an industry, if you're going to be in industry. Now for research, you probably want to know those mathematical details. If you're going to be industrial, you're going to build. This is what really all you need to know. And using a tool like Keras, you can actually build intelligent applications and deploy them out there. So I hope Pat that kind of answered what Keras is. But we will see it in use actively now in the moment. So I just imported the layer module of the Keras package. And then we are going to use the Cypher10 dataset. So previously, when I began to do this, I will have to come over to Cypher10, download the dataset, maybe the Python version, take it. But that has been, Keras has exposed an API for doing that, right? So I could just say from tensorflow.keras.dataset, import Cypher10. So it makes life a whole lot easy. Now, the next thing we would do is let us, okay, give me a second. Okay, connecting. Anyway, it's the first time I'm running the code, so I suppose subsequent runs will be faster. Okay, so my import is all good. Now, the next thing we will do is to load the Cypher10 dataset. And we talked about having your training sets and your test sets. So in the load data model, I know we'll split the data into 50,000 images in the training and 10,000 in the test. Right, so let's do that, and then your X test. And the X are the features, while the Y is the target. And that's really what you see is a convention in all of machine learning. When you talk about your X is your feature matrix, or your X, a set of features. And we will see what are features when you talk about image data. Now for okay, I think Okay. Okay, so let's pull up. I would just refresh this. Actually, it's loaded in memory in this location. Okay, so we have the X train and we have the Y train, and we've loaded the data. Now, just to show you what is going on here, I will. I think I want to get. I would like to just visualize the data so you can see it. Okay, so we would use, let me bring in Matplotlib. So Matplotlib is a Python package for visualizing on a notebook. Well, notebook or not, it's a Python package for plotting, creating plots of visualizations. So just put a comment there, that's for visualization. From matplotlib.pyplots. That's plot, what did I do? If I did syntax, right? Oh, no. Imports, rather. Okay, nice. So we know what the class names are, but I just want to, I think we had that we have an airplane, automobile. So this is just the code to visualize it. So you can see that this is nothing more but image data. And I will say a little bit about that. Import pipeline as well. Yeah, thank you very much. Hats, we had deer, and I think dog. I'm reading from my notes here, frog, a horse. These were the image classes that are in the self-attend data set, and then a truck, a frog, dog, frog, horse, sheep, truck. Okay, good. And those are the class names. So let us plot. I would just some of them just display some sample images from the data set. So I'll say plot the figure, and I'm going to set the figure size. Now this is not ML, this is just Python code to plot. So probably so I just want to plot about 25 images, and I want 5 rows, 5 columns, and I want to walk through them as I create all those stock plots. That's what that line is doing. And then plot.imshow will display from the X train. And I'll just take that a particular image index. And then I think that's all I need. Then I just want a label. If the label would be the class name, which the list that I defined there. And then I would say, give me the label from the Y, because the Y contains the labels, right? Okay. And I will plot the entire thing. All right. Nice. So this is your, well, because it's, remember, this is 25 by 25, no, 32 by 32 color image. So it looks pixelated, but the models are so powerful. And if you're using GPUs and the rest, you can even build, train the model with higher resolutions, maybe 256 by 256. It's really that powerful now with all the super machines we have available, including Google Colab that I'm using for running this. So you have your deer, you have your cat, frog, and bird. So all of and I doubt if my code really, there's something wrong with the code because I want the image names to show for every image, but it just showed on the last row, which is, I wouldn't waste time here. This is just to see it. But if you check something, you will realize that if I take just from the X train and I say X train 0, what you would see is a bunch of numbers. And really that's how images are represented in the computer. So it has a bunch of pixels. So 25, 32 pixels, I keep saying 25, 32 pixels across and down. And each pixel has an intensity value from 0 to 255. I can't remember. I think 0 is I think 0 represents black, and 255 represents white. So just how images are stored in a computer. So you can now see if you're doing, say you're doing any type of maybe art, maybe remote sensing, satellite imagery. So you can see how you can work and learn from images. And this is how a computer would store these images as a vector. So now you can see how you can, because when things are down to numbers, you can use all the fancy math, which we will talk about how deep learning works using back propagation to try to build an approximation model, right? So when we have tabular data, it's numbers. The variables that are not numbers, categorical, you do one-hot encoding, you bring it back to numbers. You have image data, you bring it to numbers. You have language data, text. So how are we learning from text? You build embeddings, and these embeddings brings everything back to numbers. Then you can do math on it. And that's all the math is happening under the hood, if you will. So I hope that kind of demystifies how all those things work, right? Okay, so I thought that would be helpful. So let's go on with our code. Please feel free to post a question or even just speak if you have any. So next thing we will do is we will, okay. I'm sorry, just a second. Okay. Now, next thing we would normalize the data. So remember I told you that every pixel is just a value between 0 and 255. So when you have large numbers like that, it's good to normalize the values to be within the same range. This kind of helps the algorithm to easily converge, right? So, and if I'm saying anything that you don't understand, just feel free to send a message. Because at the end of the day, when you are doing this, when you're training an ML model, there's a principle called a field of study called convex optimization. The algorithms you use are actually optimization algorithms. So whether it's your stochastic gradient descent or any other algorithm of that nature, you're trying to converge. So you have a bunch of numbers in some hyperdimensional space, and you're trying to kind of see how can you train the parameters of a model that will give a good enough fit to your data in that space. So learning what the parameters of that model would be, you will need a optimization algorithm to help in that. Now, if your numbers are wide, it's just much more difficult, takes more time for the algorithm to learn, to converge. So when you scale it, it's easier for that convergence to happen. So that's why we are going to scale. So we just typically scale by 255 so that every pixel value will be between 0 and 1. And so any pixel that is 255 that is very white will be 1. And then others would be some real number between 0 and 1. So it makes life easy. Okay, so X test is going to be equals to X test over 255. Then the next thing is we would now, let's define our CNN model. So let's build the model. So we define the CNN architecture. And we're going to say that using Keras, we're going to use the sequential model. So sequential model for Keras, it's just you build similar to this image we saw. Okay, my slide is, can I open my slide on? Let me try to open my slide on the browser. So it's easy to, so if I open with Chrome, easy to move from a slide to, just give me a second here. And Google Chrome. Okay. How can I close this side? Okay. So a sequential model would typically try to build one layer after the other, something like what you see here, right? The input layer, then all the hidden layers in order, and then you have an output layer. Now you can have models don't, an architecture doesn't have to follow this sequence. It can be it can have all sorts of branches. It's very interesting architectures out there. Then you can use different Keras API called the functional API, but sequential is good enough for what we want to do. It's just fantastic. Okay. Then the first layer, we are going to have our input layer, which is going to be a convolution layer as well. So layers dot conv2d, and we're going to pass in the filter. Now I did not, that's interesting. Okay, maybe when I call all of this, I will explain a bit what these things mean. Then we'll have a kernel size of 3 by 3. And we will have an activation of ReLU. Now, it so happens, so we would consult that I think it's just going to be easier that way because I have a bunch of pictures. Just give me a second now. So I'll open this on Chrome, with Chrome as well. And Chrome. Okay, so I wrote a book on this topic. So I had a bunch of pictures that I think would be very helpful. So if you come over to convolutional neural networks, and the book is publicly available, and buying it does not make me rich. So if you want it, just maybe send your email to the organizer. You can send me an email. I can just email you and you can share it around. Yeah. So convolutional neural networks. Yep. Okay. Let me come there and then I will. So we have an activation function, which is the ReLU, and we know that our input shape is 32 by 32 pixels. Now, since this is images, we are going to have 3 bands, the red, green, and blue. Or input shape equals to. Okay, so this is the first layer. And so let's start with, let me come over here. So we could see, look at something about, now, remember I showed you the representation, how pictures are represented on the computer. So this is a grayscale image. That means it has just one band, it's black and white. But the different pixel intensities is either 0 or between 0 and 255, right? So the areas of white, I look at the top left, you have 251. The darker areas around the middle of the picture, you have a 67 and stuff like that. Okay, now a colored image has different bands. You have the red, you have the green, you have the blue, and they all have different pixel intensities. Okay, now one thing to note is the idea of let me just come over. So we have the idea of filters. So a convolutional layer, which is what we called, is made up of filters, something called filters. And these filters create a feature map. So you pass a filter over an input image to capture specific set of features. And that process is called a convolution, right? And the output of a filter is a feature map. But now you can understand why we have 32 filters. So this is just saying that in the convolutional layer, we are going to have 32 neural cells, neurons, if you will, 32 neurons in that layer. So in this image, you have 4. Think about having 32 of those computational units, and they're doing something, right? I'm just talking filters, but they're actually doing an affine transformation. They are computational units doing some calculation. Okay. So that's I'm just picking things as we need them, and the kernel size is 3 by 3. So each filter. So the idea of convolution is that you're applying a function to extract information from a matrix, right? And the function is applied, so it's applied the window through the matrix, and this is called the filter, convolutional filter, or the kernel. So what's the size? So we are doing the kernel is of 3 by 3. So say you have a set of 32 3 by 3 matrix that are scanning the image from left to right, and is learning representations from that image. So that's an example of a 3 by 3 filter function. Now, I don't want to go deep into computer vision because these things mean something. There are types of filters, and they do a particular set of things. Okay. So having understood that, let's add a second layer. So this is the input layer, and I will have one other hidden layer, another input layer, and another layer, sorry. And it's also going to be a convolutional layer. You know what, I can just copy this one. And we would have more kernels, more filters. We use 64 of them. Now, how did I arrive at these numbers? It's trial and error, right? So you look at the performance, and then you can adjust it. These are parameters you can adjust when you do your hyperparameter tuning. We're still going to have a 3 by 3 kernel, and still using the real loop activation function, but this is not an input layer. So I will take this out. And we're going to have another interesting layer just because I want to talk about it. It's called the max pool layer. So I'm going to add a max pooling, and the pool size is going to be 2 by 2. We're going to flatten. I'll just type them all out, and then we will talk briefly, and then we will run the model. And finally, we're going to add a fully connected layer, which is also called the dense layer. And it's going to have 128 units. And we are still going to use the ReLU activation. And our final layer, which is so we've done the input. We had a couple of hidden layers. In this case, we had a convolutional layer, a max pool, and then we flattened it. So convolutional layer, max pool, and then we had a dense layer. Then the final layer, which is the output layer, is what I'm going to type out now. Now, this is also going to be a dense layer, but it's going to have 10 units, symbolizing that we have 10 classes. And it's a different activation function we would use here. We use the softmax that kind of less probability, the odds that that a particular observation belongs to, the odds that the data belongs to a particular class, either of these 10 classes. I will briefly explain that in a few seconds. Okay, so let's go through it. So in the first convolutional layer, we have 32 filters with a kernel size of 3 by 3. The activation function is ReLU. And really what that is, the ReLU activation function is simply another word for the rectified linear unit. So it's one of the most commonly used activation functions in neural networks. And you see it in CNNs here, and even in RNNs. Now, it's simple and it's an efficient function that can help the neural network converge faster. So, and one of the advantages of the ReLU is that it is nonlinear, right? So it allows the neural networks to learn complex functions. And from empirical work, we have seen it perform better really than other activation functions, such as the sigmoid function or the tanh functions. These are other popular functions out there. So, yeah. So it's something you can, there's more to discuss about this. I'm just saying what is necessary without diving into some details that may not be useful for now. But it's something you want to read up of activation, the ReLU activation unit. So now the softmax activation function. Now what the softmax does is it is used in the final output of classification models. Now the softmax performs, I won't explain it in the way that doesn't like it transforms the output of a neural network into a probability distribution over the output classes. So it kind of takes a vector of real numbers as input, and it returns a vector of the same size, but in this case, every element is a probability between 0 and 1. So yeah, so the output value of the softmax function is sum up to 1. So it's suitable to use as probabilities. And for a particular class, you can then know, so when you do the softmax, you can tell which class has the highest, for a particular input. So you have an image, and in the output of the network, you apply a softmax, you can tell which class has the highest probability of membership, right? So that's why we use the softmax function in the final output of the fully connected layer of the neural network. So again, it converts the output of the network into a probability distribution over the possible output classes. And then the class with the highest probability is selected as the predicted output of the model. Okay, so that's what we're doing here with the softmax. Now, is this anything I have not explained? Okay, the max pool. Okay, so the max pooling layer. Okay, very interesting. Let me actually pull up this and the feature mouse, then the pooling layer. Okay. So the pooling layer, in this case, there are a bunch of pooling layers, but max pool is the most popular one, if you will, depending on what you're trying to achieve. But the goal of the pooling layer is to reduce or to downsample the feature map of the convolutional layer. So this is just a way of learning different representations from your input image. So it kind of summarizes the input features in the length in the previous network, in the previous layers. So it's kind of summarizing what we've learned in these two convolutional layers that came before it. So these are the previous layers, and then we have a downsampling layer called the max pool here, with a 2x2 kernel size. Okay, so it kind of does some downsampling, so that consolidation. So there are things that there are various functions the pooling layer can carry out, like the max function, the sum function, the average. But we are using the max function. That's why we are using the max pool. So that I think that's sufficient for this to explain it. And I have some graphics here that you can see exactly what it's doing. So the max of these 4 pixels here in a 2x2 pool is 255. Then the pool will stride. Okay. And then the max of the next stride is also 255, and then stride, and it's 1. So you see you're condensing this set of metrics here into a smaller matrix by using the max function. I hope that makes sense. Okay. So that is that. Then we have the flattened layer. Okay, what this does is just a simple layer used in convolutional neural networks. So what it would do is it will convert the output of a maximal layer or a convolution layer into a one-dimensional vector. And then you can pass that vector as inputs into the fully connected layer. So that's why we have this operation here. So this is the canonical structure of the CNN architecture. And if you use this, you can expand this now, right, to learn other more complex problem spaces. But let's run this model and let's see how it does. Okay, so I've defined the what's going on? Okay, not units, but this is units. Okay. Okay, then let's compile the model. So we'll have a model.compile. And you're going to, I talked about an optimization function. So we use an optimizer called the Adam. I'll explain that shortly. And the loss is, we will use the categorical cross entropy. And we want to know what is the accuracy. So we use the accuracy matrix. Okay. And so this is so we define the CNN architecture, we compile the model, and then next we will train the model. No. So let's see the summary of the model. No, actually. So just a summary of what we have built. An input layer, we have a second convolutional network. And then you can also see the number of parameters in the model. But I wouldn't talk too much about this, but this is an interesting summary to have in when you have put together, designed your model architecture. Now, next is we're going to train the model. So we use a method called the model.fit, and we want to fit on the X-train dataset, the training dataset, and we will evaluate on our, we're not going to evaluate yet, we are training. And we have an epoch that tells us how long we are going to train this for. And we would validate this on the test set. So it trains, it will validate on this, on the test data set. Typically, we want to have an evaluation and keep the test set out of this, but this will suffice for this example. And after training, we will evaluate the model to see the test loss and the test accuracy. But but just before we train, we want to, okay, optimizer. And I don't know, let me see if I have, okay, we still have some, because this could get a little bit tricky to explain. Let me see if I have some pictures that will help. Because getting the concept, the paradigm is what is important to me. And then you can pursue it deeper if you're interested. So if I come to deep learning, okay. So I've talked about the, okay, Adam and the rest. You know what? I could just search for Adam. This. Okay, momentum. That's what I'm looking for. So adaptive learning rate, like the Adam. Okay, so this picture helps me to discuss about optimization. So the idea is, okay, how do I begin? Okay, let me just talk about Adam. It's in learning, what it does is, if I just realized, what is, let me have a show of hands, because I don't want to keep going down. I'm not thinking I need to explain what a learning rate is, but I want to keep this. Okay, let me just talk about optimization for gradient descent, and then everything builds on it, right? So gradient descent is an optimization algorithm that the goal is to minimize what we call the cost function of a machine learning algorithm. So in this case, we had a cost function, which is the loss, is the sparse categorical cross entropy. We will talk about this later, but a simple cost function could be your say, for example, let's say you have a root mean squared error, right? Very simple for regression problems. How you want to tell the difference between what you have predicted and the true value. And if the difference is small, that means you're doing well. If it's large, then you're making a large error. So there are more interesting cost functions out there for different sets of problems. So you want to minimize it, and just want to minimize the error, the cost of the model, right? So really the sense is the optimization algorithm for that. Now, I would explain a few things about this. Now, what we will need to learn is that in the final analysis, you want to kind of learn the lowest point in a feature space. And this feature space, think about it as having like my background, you see a mountain and hills, and you have a feature space. You don't know what the feature space looks like, but can you find the lowest point in that feature space? And the lowest point, in principle, will minimize the cost function. You have the lowest error. And you're somewhere on that space and you're trying to walk down the hill, right? To find the lowest point. And the number of the length of steps you take downhill is called your learning rate, right? So if your learning rate is large, you make huge steps, but you can also miss the local minima. You may miss that lowest point and not find it. If your learning rate is small, you take small steps downhill. It will take a longer time to converge, for your algorithm to converge, but you will most likely find the local minima, the lowest point on that feature space. So that is an idea of what optimization is doing, and when we talk about choosing a learning rate. Okay, so having said that, so there's an example of having a large learning rate. So you're not finding the local, you're just bouncing around. A smaller learning rate will take more time, but you probably optimize. You probably converge. So we have all sorts of optimization algorithms, and one of them is the Adam, which I was just going to talk about. Okay. Okay. So that is an adaptive. So adaptive learning rates is an example of it is your Adam, which we are using. So what it does is it readjusts the learning rate in accordance with the training data. So for each parameter, it adapts the learning rate as it trains. So that I think is suffice to know for this exercise. Okay. And so let's train the model. So we can get some real-time metrics into how our model is performing. I typically like what I'm seeing in that I'm seeing the loss going down, 2.0, 1.97, 1.9. So that's good. And I can see our accuracy improving. It was 10%, 20%, 30%. And I know because this accuracy is going to be good because I'm evaluating on the test data set, not on the same data set I use while training. So this gives me an idea of that, okay, my model is doing well on the test set. If your model is doing well on the test set, that means that you don't have high bias, so you're learning, so the accuracy is still improving. I like that. And you don't have high variance. So high variance is that you learn so well on the training set, but perform poorly on the test set. The test set is steady, the accuracy is steadily increasing. So that looks good to me. So let's see. So while this is training, I just stopped to see if you have any questions before we go on. Okay. If you have any, please feel free to put them on the chat. Maybe I should have used the GPU runtime. But anyway, that's fine. Okay, there's a question. How did you pick the layers when defining the CNN architecture? Okay, so there are various ways to pick a layer. You could use, okay, thinking about it from scratch, this is a sophisticated means that, well, you have some method to your madness, but it's just a glorious trial and error. If you think about it, a sophisticated trial and error. You don't know upfront, right? And so I've always wondered, why does it have to be 32? And you see it grows by like the number of bits. I've seen 8, 16, 32, 64, 128, 526. I don't know. So it's trial and error, right? But the more filters kernels you make in a layer, the layer is much, much expressive. So you can quickly overfit and it will be useless. So you have to really balance things. So it's an art of coming out with this particular architecture. And I think I can extend here to say this is why really some of these companies bringing out these state-of-the-art models, they have millions of dollars spent in computation because you're doing this over and over. Now, just see the amount of time we are waiting to see our model train. For something much more complex than this could probably take a long time to train, and we are using a CPU. And if you have GPUs, you have much more powerful computational and powerful machine, you can get this training done faster. And because it's highly iterative, you know quickly what does not work. You can adjust the layer in a process called hyperparameter tuning. Now, but I wouldn't, if you're not into research and trying out things or even adding some custom components, you just want to use, they are blueprints, they are canonical layers that work. So you could check the TensorFlow website. What are some of the layers used for problems that you're trying to solve? Or research papers. And you can use layers that researchers have already tested and they've done ablation studies. They say, okay, fine, for this problem, this is the architecture we use and it gave us good results. You can mirror that instead of doing all that, finding out trial and error yourself. So there are just some canonical examples for neural network architectures for CNN and for CNN, RNNs or whatnot, and for different problem spaces. You have these sample architectures that you can copy it and use that as a starting point. And if you don't like it, you can iteratively begin to change things as you test your model code and see how it performs on your particular data set. So we're up to the second epoch, and okay, we are the third now. So I'm seeing something, my accuracy is increasing, or actually, not just my value, okay, on the training set, is increasing. I like that. My accuracy on the test sets from the first epoch to the second epoch increased. I like that as well. So I like what I'm seeing. Now, there are a bunch of other things we can add to this model. In the training, we can add to the training code things like early stopping. And I find early stopping to be important in the sense that as we go from one epoch to another, once we are not making any gain, whether the loss is dropping, once the loss is not dropping, or the accuracy is not increasing, the training procedure stops. And that final model is saved. So I find it to be very useful. So those are ways you can enhance your training code. So this is why I think Keras is just a very nice tool to build, to do deep learning, right? And that's what we've been doing. So I like this run. Probably I should have set a lower amount of epochs. 10 is too much. I don't think we will wait for 10 epochs to run. So what I would do is I will stop this. And if you're new to Collab, it's really powerful in that I can use a GPU, right? So this should train faster. And I'll change my epochs to probably four epochs. Yeah, connect real time. Yep. So I will just run everything. So we don't have to wait till it gets to 10 and we have more computational power. Okay. Okay. Let's get the training started. I mean, just visually, you can see the training speed. Now, it just shows you the difference between a GPU and a CPU. Right? We need to pay for all those GPUs. If you're watching, just observe the speed in which it's going epoch by epoch. This is a lot faster. And, really, we can even go up to 10 because this is like living, going from 20 kilometers per hour to 100. It's just a lot faster. Okay, so we've trained the model and we are up to 67% on the test set. Not bad, better than 50-50, better than 50%. So I take this, right? But let's get this up to 10 and see if we improve their performance. Give me a second. Interrupt execution. Anyway. Yeah. Let's have 10 epochs. Let's see. Okay. So happy to take any other question. And I think I think after this, we will take questions. If we don't have any questions, I think we can wrap up here. There's just not enough time. Recurrent neural network is a whole lot of new things to talk about, a whole field on its own. Or maybe we just run an example and we see how it works with that. But I think we can wrap it up here. Maybe I'll do a different, more interesting example, and then we can close. Okay, so on my training set, I'm getting up to 96% accuracy. So it's doing well on my training set, right? But on my test set, it's just 66%, then 57%, and it's like that. The accuracy is increasing on the test. Now it's down to 66, so I've peaked, right? We could do certain things to see what we can do. So the model has almost 100%. accuracy on the training set. When you bring the model to data it has not seen before, I'm averaging 65%. So this is critical why you must separate your training, your evaluation and test data from your training data. So you can tell if your model can generalize, can learn in new examples. So really all we are getting here is 65% accuracy. So what are ways we can improve this model? I think that's what we'll just do before and then we can wrap up from there for the remainder of the time. Let me just complete the running. Okay. Now, there are a couple of things we can try to improve the model on the Cypher 10. So one is we can increase the depth of the model. So we can add more hidden layers, right? So we can add more convolutional opponent layers to increase its depth, right? So we have that's why I call it deep learning. That's where all that comes from. I don't think we need data augmentation, but that's something we can do where you apply random transformations to the training data. But I don't think this data is a well-curated data. It has all sorts of augmentation. I don't think that's what we need to do here. Batch normalization is another thing we can do to normalize the inputs to each layer, right? We normalize the data before starting the training process, but at every layer, you can normalize the inputs of when you have the output, which is the feature map, you can normalize it before sending it to the next input. Okay, that's something, or you can use dropout if your problem is overfitting, which I think we have an overfitting problem. So we need to regularize. Now, so let's see. Maybe let's do after what we could do is, let's see the impact of this. So we have a 32, we have a 64, 128. I could just throw in, actually, yeah, I could throw in the dropout layer. So where am I picking where to add this? So the question that was asked, it's is an art, right? So you have to try things and run it and see what happens. So 5% black out some of the inputs, and I'll also add a dropout here, and I'm going to call it kill 25% of the features. No, not features, sorry, of the filters or panels. And let us try to run this again. And I would drop these two. I will reduce the number of filters as well. And I'll make it 64. Okay, so I'll compile the model and let me leave this information here and just train a new one. And then let's see. Okay, increase my screen. So we have starting the model, okay, validation accuracy, it's going up slowly, but the goal is we want to see if we can go beyond that 66%. And you can also try batch normalization, but let's see. So even if you get to 10 out of 10, at least I like that the validation accuracy is steadily increasing. So I could just increase the epochs. And maybe I'll just increase it to 50. And let me add early stopping so that we can, this is up. So this is steadily increasing. So what I would do is I'll run this again. I'll increase this to 50. And what I will do is I will define early stopping before training the model. I think it's something useful. So what I'll do is stopping. Oh, I have to define it early. I think it's called early stopping. And I'm going to monitor the validation loss. Let me import it first. There's a callback. So from TensorFlow .keras.callbacks, import early stopping. Nice. And okay. Did that look good? And then in my code, I would say that I'm going to monitor the validation loss. So monitor, let me just copy this here, validation loss. And I'm going to set my patience to 5. Okay, and then in the model.fit, I will add a callback. Validation data, I'm going to add callbacks equals to early stopping. Okay. What is this? It is import this from me. I don't need that. What's that? Okay, let's see. Between the first 20 epochs, we would definitely know if our validation accuracy is increasing or not, and we'll know what to do about that. Hey, no, hold on here. Let me define. So yeah, reset the model, define the architecture again, compile the model again. That's important. I'm leaving the old results just to compare, and then we will run this. Because if we don't compare, it will just, it's improving on the same model. Good, so the accuracy starts from 20%, 10 to 6, that's fine. Okay. Okay, so you see the model increasing, that is good. And the validation accuracy is what I'm putting my eye on. The training accuracy is going on steadily. It's slower in just how quickly it's learning, even on the training set. Which is good. I like that because we've regularized the model. We've added those layers that will penalize the model to restrict how quickly it's learning. We added the dropout layers. So it's fantastic. So it's we are up to the 9th epoch. Previously, we were overfitted. We're up to 97% on your training set, whereas just averaging 66 on the test. I'm not even improving at all between epoch 9 and epoch 10 for the previous model. So really, this workshop is hands-on in practice. You see how we think about these things, right? We've added regularization features into our modern architecture. It's still going to train, get up to the, hopefully we would see, but just the speed in how it learns is reduced. But hopefully over time, we can learn a better model. So I'm still observing it. My loss on the training set looks like it's dropping. And the accuracy is increasing steadily. On the test set, actually I'm getting better better accuracy performance on my test set, which is interesting. So let's see. So I've gone from 64 to 65. Let's see what's going on. It's very good. So this is the first time this is AI modeling. And we're teaching the computer in this case to learn how to identify pictures. You could tell a horse from a cat, from a truck, an airplane, and things like that. So we are up to the 60% on our training set. Validation set, I'm a bit worried because we've gone from 65 to 64. I hope we've not plateaued on the validation accuracy. So I'm not seeing too much of an improvement there. Let me see what my early stopping is monitoring. It's monitoring the loss. Okay. So it has stopped. It stopped the training after 24 epochs. And now this is the beauty of early stopping because I don't have to sit there monitoring my code. If you have a really large expressive training regime, right? And you put early stopping, if it's not improving anymore, you don't want to waste that computational power, stop the execution. So we can play around with this and seeing how we can improve this. So we're still getting 64, on average 65% accuracy. There are things to do to get this improved, and it's a trial and error. So this is a machine learning engineer or a data scientist at work. And that's that. Okay, so I will wrap up here. Now let's just to wrap up this code nicely. Let me delete this. So finally, I want to reduce the size of my screen so I can see other things. Okay, so now we have a model. I'm going to keep this up here. Let's evaluate the model on the test set. We've seen that already, right? Because we had our we passed the validation data into the training, into the model.fit function. But we've trained, in this case, we have a model. So we'll use the model we have trained to do a one-time evaluation. So evaluate the model on the test set. And we want to get out the test loss and the test accuracy. So we'll call the model.evaluate. So this is the model we've trained. Now you can save this model. And if you're going to deploy, this is the model you will deploy on your web server and expose APIs. And so if you're using your cell phone or you're doing any app that has some machine learning, what you're doing is you're sending, making an API request to a deployed model on some server. And there's the process in which they train that model. So model.evaluate X test, Y test. And I'm just going to print out the test accuracy. Test accuracy, I'm going to print this test ACC. And let's do that. So we have a test accuracy of 64%, as I knew it would be, because we had that validation part of the model training procedure. Okay, now, assuming you have a model, you've trained it, you've evaluated it, you like what you see, you want to use it to make predictions. So let's make a prediction now. So I'm going to make predictions, on new images, right? So predictions equals to model.predict. And we're going to take a sample image from our test set. We'll just take like the first 5 images. Now, we've done the visualization before, so you know that this is an image. So let's see the prediction, but I'm going to do something much more interesting. Where's my plotting code? I can use this code still. I just want to plot. Actually, let's do this. So, okay, let me run the prediction first, right? And you know what? Let me print predictions. Okay, this does not make sense. This is just the probability output. I want to tell the class it belongs to. Give me 1 second. I'm going to okay. So what I want to do is show the predicted classes. I need to anyway, give me a second. And so I need to find out what the predicted classes are. So remember, softmax gives you, so for all these 10 vectors, it gives you a probability that each image will belong to a particular class, right? So we want to take the maximum. Which class has the maximum probability? And that would be the predictor class. So since I know that this is the list, I will just use a function called my argument to maximize, arg max, and I'll pass in the predictions. I'll just copy and paste. Pass in the predictions, and let it be a numpy array. I don't need to do anyway. Whatever, so long it gets me. No, dot prediction. So for each prediction in prediction. So for those of you familiar with list comprehensions in Python. Okay. I've done that. So I will print my prediction classes. I'll still print out the prediction so you could just see what's going on. Print predictions. And actually, let me do this in a new cell. Print predictions and print for each 5. So there are 5 images I want to predict. CTED predicted classes would be, and I will just use this one here. So 31806. That's what I expect. But you need to know what 3 is, what 1 is. So I can map these actually to get the class names. Yeah. Give me 1 second. I have my names here, and I know that. Just a second, let me tidy this up. And so I know for all of this is going to maximize and it gives me the class, and that's fine. So maybe printing the project class names for the first 5 images. So what I could pass this, if all of these are, and I know my class names, I define my class names here. So yeah, what the heck? I can pass all of this, right, into, so I just treat these as numbers. It would simply get at the index. So I will say class names and I will put this as an array. That should work. I think it would. So let me run this. Printer predictions, printer classes. Beautiful. Now let's have a visual. Let's see what the real images are, because now I don't know if I'm correct, right? So let me print out these first 5 images and we can tell with our eyes what the images are. Let's see. So I'm going to plot the true images. Not true, but the images. Okay, I just put the images and predicted classes. So I just I'll put it in a subplot the way I did it previously. So in this case, I know that there are 5, so I probably just want one row and 1 row and 5 columns. A figure size 15.3 is fine. Okay. And for I and axis, I'm going to go through each subplot. AENUMERATE. And then I am sure, which is the code I had previously. And for X test, and I know it's 5 because I want 5 images. So I will just put X test I, and I'm okay with that. And I want to set the title, which would be nothing more about the predicted classes. Well, I'm not sure. Well, if the title will know if it's wrong, right? What we would know from our eyes. And ax.axis is off. I think ax dot set title. A.axis. I don't want any axis. Just want to see. And then plot everything. Okay. Looks good. So let's see. Plot n row. No, n rows. This would be S. Okay. The frog is correct. Airplane looks correct. Ship looks correct. Automobile, I'm not sure. This doesn't look like and looks like. I mean, the image is 32 by 32 pixels, right? So it's not exactly the correct. I can't tell. Looks like a ship to me. For cats, I can't tell, but it looks like looks like a cat to me. But we can say 3 out of 5 concretely. Anyway, thank you very much. This is an end-to-end workflow for building an image classifier with deep learning. And in this workshop, we used convolutional neural networks. I hope you're able to learn something about what machine learning is, what is deep learning, and how we can use it in terms of fitting your problem into either of this paradigm. This is a supervised learning framework, and we use the convolutional neural networks for this image classification problem. I hope that just like we do with machine learning, you can take what we've learned here and generalize to your own problem spaces. And I wish you the best in your machine learning journey. So I want to hand it back to the organizers. Thank you so much for coming and spending the time with me. I appreciate it. Okay.